Welcome everyone to our last lecture of this course. So last time we discussed how to solve matrix models in the large n limit. So one thing I wanted to mention, by the way, something that maybe wasn't very clear. So from last time. So we looked at how to count graphs with quartic vertices. So, and we saw from the solution of this one matrix model how one can count the number of graphs with n quartic vertices and the spherical topology. So it's a bit weird to say that we have graphs with quartic vertices. So what's more standard is to think about quadrangulations. But what I wanted to mention is that it's actually the same. So when the number of graphs, number of these graphs, like with n vertices, well, and let's say fixed topology, spherical topology. So these graphs are in one-to-one correspondence with quadrangulations of a sphere into n plaquettes. Well, with n plaquettes. With n faces. So the reason is very simple. It's just for any graph, we can consider what's known as its dual graph. So if I have some, well, let's say some graph looking like this. Then what I can do is I can define a graph whose faces, whose vertices are the faces of the original graph and vice versa. So in other words, what happens is into each face of the original graph, I put a dot that's going to be the vertices of the new graph. This will be what's known as the dual graph. And then I connect the vertices which share an edge. So I connect the vertices of the faces that have a common edge. Like this, here, 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 and so on. So you can see, for example, here I had a triple vertex. Now in this graph, I will have a face with 3 edges. Well, here this was a quadrangular. Well, here most of the vertices are triple, but then vice versa is also true. So here I had the face with 4 edges. Now in this red graph, I have instead a vertex with 4 edges. So the valences of the faces and vertices are just interchanged. That's a useful thing to know. And so here for us, what's important is that counting graphs with only quartic vertices, if I build the dual graph, then it will have only quartic faces, so only quadrangular faces. And these graphs are in one-to-one correspondence, so it's the same thing to count both of them. So in matrix models, we assign couplings to the vertices, whereas we don't assign anything to the faces. Actually, there is a way to deform the model in a nice way, such that you also would have couplings for the faces, but we are not going to go into this. So that's one comment I wanted to make. So another comment is, so last time we looked at radius of convergence. So we had some series which was roughly something like G over G critical sum to the power n, well, times some weight. So which was related to the number of these graphs. I just want to make the conceptual point that when we are, so why the radius of convergence is physically important. So when G goes to G critical, so when we go close to the radius of convergence of a series, then the series will be dominated by terms at large n. Because truncating the series to any finite number of terms would give a absolutely convergent series. So that any divergences come from terms corresponding to the tail of the series. And physically, that means that we are looking at large graphs. So at graphs with many vertices. Remember, this n was actually the number of vertices. So just one point to reiterate why these limits are particularly important when we go to the border of the convergence region is because there it means that we are looking at the terms with large n, that is at large graphs, and that is what corresponds to quantum gravity in some sense. Okay, so these remarks, just to wrap up what we did last time. So today I want to discuss what's known as topological recursion, or at least sketch what it is. So this is a way to discuss 1 over n corrections in a very nice and geometric and uniform manner. And so this is in particular what is very important in JT gravity. So that's how one can identify JT gravity with the matrix model by showing that the partition functions satisfy the same recursion in both cases. And that's so this is an idea which is usually presented in some very mystifying way. If you read some reviews by people who discovered it, like Einar or Antan, and probably some more people. So they sometimes present it as some insane miracle, which, okay, in some cases maybe it is, but in matrix models it is quite intuitive to understand. So we start from a very simple and important in general idea, which is known as loop equation. So these are going to be equations relating different correlators in our matrix model. So remember when we have our partition function, that is the integral over Hermitian matrices, e to the minus n times some potential. So we can consider correlators like trace m to the k, so which is the same integral with this insertion. So here better to say trace v of m. Trace m to the k, e minus n trace v. Well, normalized by the same integral without the insertion. And then one can consider multiple insertions like trace m to the k1, trace m k2, and so on. So these are going to be the basic observables. So these loop equations, they relate different correlators to each other, and they mix different orders in the 1 over n expansion. So their origin of these relations is very simple. They are basically the Schwinger-Dyson equations familiar from field theory, or so to put it another way, they express the fact that the integral of a total derivative is 0. Or to put it yet another way, they express the fact that in an integral we can always do any change of variable. We can rename the integration variable in any way. So we will derive them in a second. Just I want to say what we're going to do. So Schwinger-Dyson equation. And the same as saying that integral of total derivative is 0. And the same as redefining the integration variable. So in the second, well, these are all just different names for the same thing. Well, so concretely, to derive one of them, let's consider a particular, so it's a particular integral of a total derivative. So let's look at this identity. So integral dm d by dm ij of m to the k ij e to the minus n v trace v of m. So this is 0 because it's the integral of a total derivative. I am differentiating this expression in a particular matrix element with some indices I and j. Well, I could leave it like it is, but then I'm also summing over I and j so that I get some expression with all indices contracted. So this is a trivial identity. Any integral of a total derivative is 0, well, when the integral is convergent at infinity, which we assume here. So let's see how this gives some relations between these kind of correlators. Well, that's quite easy to see. So one just has to understand what is this object. When we differentiate this product, we can differentiate either the first term or the second one. So and then we get some structures. So this first one, well, so let's do a couple of examples to see what it is. So d by dm ij, let's say k equals 2, so m squared, k equals 2. So that would mean we have m, let's say I a, m a j. Right, so m squared with indices ij. So when I differentiate, I can hit either the first one or the second one. So suppose I hit the first one. Since I'm differentiating these particular indices, that means A has to be equal to J. So, well, and then differentiating the first one is actually gives 1. But A has to be equal to J. So I get 1 times M J J. So, or I can differentiate the second one, then differentiation gives 1, but A has to be equal to I, so that gives MII. So then you can do the same exercise with K equals 3, and then you find some similar expression, and then you spot a pattern, and I leave it as an exercise to show that d by dmij of this thing, mkij, is equal to the following. So we split this k into 2 parts. So, well, here it was just 2. So we split it into a part that's, so 0, 1, and 1, 0. But in general, we can like put this derivative into any place among the k possible places, which will give, in each case, a slightly different result. And the result can be written like that. Sum L to from 0 to k minus 1, m to the power L I, m to the power k minus L minus 1, j, j. Well, here it's, so the term with L equals 0 would be this one, m k equals 2, L equals 0, so m to the power 1. J, it is this, and the second one would be L equals 1. So, well, in general, it is more or less intuitively clear that when I just differentiate in some place, then I basically get the trace of the left part times the trace of the right part. Any questions here? It's a nice exercise to derive it by whatever way you like. So this is one thing we're going to need. So the second thing we will need is how to differentiate this factor, d by dmij of this exponent minus n trace v of m. Well, it's going to be the exponent itself so times the derivative of the potential. So v of m is just some function like t2 m squared plus t3 over 3 m cubed and so on. So how to compute the derivative of such a function with respect to one matrix element? Well, for instance, m squared. Yeah, and then we take the trace. So let's try it on the case of m squared. So d by dmij trace m squared. So that's d by dmij. We can say mab, mba. So that's mab, mb something would be m squared, but then I have to contract this index here to get the trace of m squared. So, well, then we just differentiate. So in the first case, so I get a equals to I, b equals to j. Differentiation gives 1, but then I have to plug the indices here. So that would be m, what's weird, ji. And apply, then if I differentiate the second one, it will give the same contribution, as you can easily check, so it will be just times 2. Well, and the structure in general is that, so this 2 is just the derivative of this function, x squared, times, well, it comes from differentiation, and then this is just the derivative, but with the indices ji. That's important. Well, and so here what we get will be, so this exponent times v prime of m with indices ji. Well, if you want, you can easily check it for the cube, for example. Just an exercise in differentiating with these indices. So, well, so like I said, if m is, let's say, just trace m squared, so then that we just checked this relation. Derivative of this v of m would be, so v of m itself is m squared, so derivative would be 2m, so 2m with indices ji. That's exactly what we found here. Well, this is kind of quite natural because we sort of differentiate with respect to the last matrix that appears here, and then it is contracted with the previous one, but the indices have to be in agreement. So ji times our mij. That's why we have ji here. Okay, so right, so we are differentiating this. So we learned how to differentiate both of the pieces, and yeah, minus n. Yes, sorry, yeah, that's a good point. There will be m minus m. Yeah, times m minus m. Yes, thanks. So 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 we have 0. 0 is going to be the sum of two terms, derivative of that and derivative of this. So derivative, and remember, it's all under the integral, so we get averages. So derivative of the first one, so this is just trace m to the power L and trace of m to this power, which I can write down. Sum L equal to 0, k minus 1, trace m to the k, trace m, what was that? K, m to the L, k minus L minus 1. So it will have to be contracted with this. So we are doing d by the mij, and and here we had mk with indices ij. So this matrix will be multiplied by this one. It will be mkij times this ji. So it will be the product of m to the k and this v prime. And then we take the trace, and the last indices are also contracted. So this minus n, I'm moving this term to the right-hand side, so I get n. And the correlator of, so expectation value of trace of m to the k, v prime of m. So this is a nice equation. So that's the first example of the general loop equations. So what's the structure? So here you can see that we are relating a correlator of two traces to a correlator of single trace, but with some extra thing that multiplies it. So the reason for the name loop equations comes from gauge theory, where one can write similar equations for Wilson loops. Or here, in some sense, one can look at each trace, at each single trace correlator as some kind of loop, if you write it as a Feynman diagram. So here we have this trace of m to the k, and what we are doing is splitting it into two traces into all possible ways. So sometimes people write it like, so this loop, well, with some extra thing corresponding to this potential, is equal to the sum of all possible splittings into two loops of different sign. But okay, these are all just words, so this is a very concrete and not too complicated equation. Yes.
When on the right into your
Yes. Yes. They are all. So all of this depends on all of the t's because we are averaging here. So this is the average. This is the integral with this potential. So it will all be integral dm exponent of potential and with these insertions. So they are all averages in the full model. Any more questions? Right. So these are, well, they are quite non-trivial objects, but there is there are those simple relations between them, and so it's one can write similar equations with more traces. I'm not going to do this here, but it's quite straightforward. You just consider more insertions from the beginning. So it's instructive to also derive them in a different way by imagining that we do a change of variables in the original integral. So let's imagine the original z. That's integral dm e to the minus n raised to v of m. And suppose I do a change of variable of the kind m goes to m plus epsilon m to the power k. So a small change of variable, small variation of the matrix in this way. So you can say I just rename my integration variable to this that I call like m tilde. But I still have integral z is still equal to the same thing if I redefine my variable, integral dm tilde equal to the minus m trace v of m tilde. So now when I expand, I plug in here what I call m tilde, I expand and I collect terms with order epsilon. I will get some identities for these kind of integrals with some insertions. So that's exactly the way that we derive Schwinger-Dyson equations in field theory, right? You consider small variations of the field, then you expand everything to this variation, collect the terms, it will relate different correlation functions. So this kind of symmetry is what any integral has. So how to compute it explicitly for this case? So there will be two pieces. So first of all, this variation, which will give something quite similar to what we had here. Well, it's just derivative of the potential. And so variation of this gives epsilon. So here I have this v of m tilde. Let's write it then. So v of m tilde is v of m plus epsilon m to the power k v prime of m. One has to always be a little bit careful because we are dealing with matrices, not to mess up the indices, but here it's fine. So, and this will be in the exponent. So we have exponent of 1 minus n this. So we will get, when we expand the exponent, this will just come down. So we will get something with correlator of, well, since v was under the trace in the exponent, we will get downstairs this trace of m to the k v prime of m. Well, exactly like we derived in the previous approach. But there will be another contribution from the measure. This change of variables is not some kind of orthogonal transformation or rotation. It's an actual non-trivial change which will affect the measure as well. So this dm tilde we have to compute. So what we have to compute is the Jacobian. One can schematically write as dm tilde by dm. So I leave to you to work out the details as a nice exercise. Just look at the indices and so on. So you see here we are changing the element mij by m to the power k ij. And then we have to take the Jacobian with respect to these indices of the matrix. Well, then use some formulas like determinant of 1 plus epsilon is the epsilon trace of this thing, like, well, so roughly determinant 1 plus epsilon a is what 1 plus epsilon trace of a. Hopefully that's right. Yeah? Yeah. So, yeah, but, well, we also have to actually take the derivative. So what we will get is 1 plus epsilon d by dmij. Well, m k ij. So the origin is quite clear. So we are taking this thing. We have to compute the derivative of the new matrix with respect to the old one. Well, so it's quite natural we get derivative of this variation in the original matrix element. And this thing we just computed. Well, it was here. Sorry that I erased it. So it will give the same thing that we had before. So it will give this term of the equation. So that's another way to derive the same equation. Well, without, so what we did before was we said integral of total derivative is 0, but okay, it's quite a weird procedure. You have to do by hand this total derivative. Whereas, so here it's in some sense more natural, just in any integral you can do a change of integration variable, like renaming like this, and this will give the same identity. Any questions here? Well, it's conceptually a pretty big point. So you see we are doing, one can do many variations. One can take k to be arbitrary. And so each of them gives a separate identity between correlators. Well, and if we had, and if we originally considered this thing times some trace of m to some other power, then we would have to replace this by m tilde as well, and it would also change, and we would get some more complicated relation between various correlators. But they are completely straightforward to generate. There's nothing mysterious behind it. So one can find actually quite a deep structure looking at this. What in fact one can find is a Virasoro algebra here behind this one matrix model. So let's consider the most general potential of the kind V of m some. Okay, so it's useful for the purposes of this discussion to start from 0 to infinity tk trace m to the k. So in this, I think in the normalization that I have here, normally we would divide by k, but let's not do it just here. You can reinstate those factors later. So then what we'll be looking at are some differential operators in these tk variables. So if I differentiate in one particular one of them, then if I differentiate specifically in Tn, then I will get dz by dTn. That would literally be the, well, up to maybe some factor of n. No, without any factor. Yeah, dz by dTn would literally be the expectation value trace m to the power n. Well, better to say d log z. So dz by dt would give me the integral with this insertion. And I want to also normalize by the partition function without any insertion. So I will have this. Then if I differentiate more times, I will get correlators with multiple insertions. And so one can check that all these equations can be written in terms of the differential operators in this t variable in the following nice way. So let me introduce operators. So I will not derive this here. It can be found in many textbooks, just to save some time. But let me write the results. So I introduce differential operators Ln, which are second-order differential operators that have a first-order part like this: k, tk, d by dtk plus n, plus a second-order part k 0 to n, d2 by dtk dtk minus n. So some very concrete second order differential operators. And the statement is that they all annihilate the partition function. Equals to 0. Well, okay, there's no, here I'm differentiating z itself. Well, log z and z will differ just by 1 over z normalization. That doesn't really matter. So by doing just the same tricks with either redefining basically redefining the integration variable, one can find these equations. So you see this, the term with d by dt would give the basically derivative of the potential, whereas this guy would give the 2-point correlators, more or less. So anyway, that's what we find. So, so this thing, so these are known as Virasoro constraints. So why Virasoro? So Virasoro, because these operators, the natural question when you have some operators annihilating the function is to ask, what happens if I commute them with each other? Well, and they form the Virasoro algebra. So their commutator has the form ln is n minus n l n plus n. So they are defined, I remind, with n greater or equal to minus 1. Well, so one of them I think is really simple to understand. Just let me see which one. So let's say, so if n is equal to minus 1, for example, so then this term is not present. We just have the sum of k, tk, d by d. Well, probably if n is equal to 0 is the same. So if n equal to 0, so then this is just some k, tk, d by dtk. So this expresses the fact that our potential is a linear function in all the tk. Well, since it's in the exponent, we do like t d by dt. But this is, well, the fact that we have this equation for n equals 0 is just a simple reflection of this structure of the potential. So these operators are, well, there is nothing that complicated about them. So they satisfy this algebra, and they annihilate the partition function. That's quite a remarkable fact, which means that the partition function actually has some kind of CFT interpretation. One can, in fact, show that it is equal to some kind of two-dimensional CFT correlator with insertions of some objects that are known as screening charges. Well, basically, okay, let me not go into details here, but it's quite well known how to write this. It's this kind of thing is useful for various applications. So these will be some charges built from some energy momentum tensor of some scalar theory parameterized by these T's. And then for some more complicated matrix models, one can get more complicated CFTs based on some Kac-Moody algebras and so on. So that's a whole direction of research that was explored a lot in the 90s. But just conceptually, it's quite interesting that you can relate this integral to a CFT. So also, yeah. Yeah, so it's not that I'm assuming, it's what I find. By computing these operators, I will not find any central charge here. But then, in fact, one can do some other variants of this construction, like, for example, take the continuum limit in some sense, and then there will appear something like a central charge. But this will bring us into some orthogonal direction, so I don't really want to go there right now. But that's a great question. Any more questions here?
Yeah, how do you find them?
L minus 1, well, just by this, the same definition. T minus 1, well, T minus 1, wait, so let's see, so d by dk, yeah, that's a good point, let me see. Well, this equation comes from variation of m going to m plus epsilon m to power n plus 1. If you consider this variation, then you get Ln. So you see n equal minus 1 is still allowed. It's like variation by m plus just a constant metric. And then, well, by looking at this, you can deduce what will be t minus 1. I think it's just set to 0. Any more questions? So one thing I'd like to emphasize about these equations, unrelated in principle to what we're going to do next, but conceptually quite important, is that they, in some sense, they determine the partition function. So Ln z equal to 0. So up to some boundary conditions and some technical things, they determine z itself. So in this, so and that brings us to some deep questions, like when you have a system of differential equations, how one can verify that the solution is uniquely determined, and more or less one can do this here. And for example, from these equations alone, one can recover the perturbative expansion of Z. If you just try to build the solutions as formal power series, you can deduce their coefficients by imposing these constraints. So these are infinitely many equations. And another question one can ask, do they have any solution at all? And well, we know there exists a solution, but one can also build it iteratively. Well, that's quite a deep observation, which also ultimately connects this to some theory of integrable systems after some more manipulations. But again, this would bring us into some orthogonal direction. So probably that's a good place to have a break. Let me know if there are any questions. Otherwise, we can do the break. Let's continue. So about this, so one can go into many philosophical discussions of why this happens. So one interesting point, just let me highlight to wrap up this part about the Virasoro constraints, is that they are, to really see them, one should activate all the couplings in the potential. So if you are looking at one particular matrix model, then okay, you will see some differential equations, you will see some equations relating different correlators. But if you truncate this potential at some order, you will not actually find these operators. You will not see that they form a Virasoro algebra, and there are infinitely many of them, and so on. So some people regard this as a deep philosophical lesson, saying that when you look at some theory, then you should consider the most general set of couplings consistent with the symmetries of the theory, and then the most nice structures will reveal themselves. Well, I mean, take it with a grain of salt, but here you can see that this, what this means in practice. Right. So now we are, can actually get some glimpse of the famous topological recursion. So for that, let me rewrite the equation that I had here. So this loop equation, yeah, so sum L from 0 to k minus 1 trace m the L trace m k minus L minus 1 is equal to whatever n trace m to the k v prime of m. So notice that this equation and everything we did so far is valid at finite n. It was just a reshuffling of some terms in the integral. So we never took the large n limit, unlike what we did last time. So topological recursion is about how to expand this equation in a nice way at large n. And what equations one gets for different terms. So remember last time we considered some objects, like for example the resolvent g of x was this integral d lambda rho of lambda x minus lambda, well, 1 over n. Was it 1 over n? Probably not, like this. So this was the, so rho of lambda was the density of eigenvalues that have condensed to some cuts in the complex plane, and this was the resolvent. So in one thing I didn't mention maybe there is that at finite n, so this object is just 1 over n, well, the object of which this is the continuum limit is the trace 1 over x minus m itself. So the correlator of this trace 1 over x minus our matrix, well, since we're taking the trace, this is fine. So it has no free indices. 1 over n is for normalization because, well, m has n eigenvalues. Trace of m would be their sum. The eigenvalues are, well, so roughly trace m is of order n. The trace of anything is of order n. And then, so when n is large, then, so to have a finite object, we put 1 over n. So, and that's the object which we learned a lot about last time. So also it's instructive to rewrite this as a geometrical progression. So this will be 1 over n. It's a, what I would say, this is a generating function of correlators. If you expand it at small x, so at large x, and then this will be some, so here one should be a bit careful with the signs and so on. So x to the power k, well, I always have trouble with this. Yeah, so like this, m to the power k, x to the power k plus 1, k from 0 to infinity. Yeah. So I think that's correct. So you see, it has, at large x, it has 1 over x asymptotic. Like from here, so when x is large, neglect this m, trace of 1 over x is just n over x because identity matrix has trace n. So if we'll cancel this n, we get just 1 over x, like here. So m to power 0 over x, this will be what we want. Yeah, well, here trace. So I should write like, this is the expectation value of the trace, m to the power k. Yeah, so this is correct. Yes. Yeah, so, well, just the sum of geometric series. So this result generates all the one-point functions of trace m to the k. It's a pretty nice object. Yeah, x is just a real number. It's just the variable we put in the input. It's just the generating parameter, if you want, and we are just looking at this series parameterized by x. The second? Yeah, here is x times identity matrix. Yeah. Yeah, sorry if that was not super clear. Just so when we go to eigenvalues, we just replace basically the matrix by the diagonal matrix with its eigenvalues. That's the reason for this formula. Yeah? So when you run yes, yes. So this, So find n that stops here, so this is at large n, like what we discussed last time. Yeah, that's fine. Yeah, so I'm averaging over matrices, but then my integral dm is the integral over eigenvalues. If I go to eigenvalues. Yeah, I'm not integrating over the rows because so the integral over eigenvalues is dominated by a single saddle point. So integral of eigenvalues to like e to the minus s of lambda. But I'm looking at the leading, so s is of order n, what we discussed last time. So I'm taking the integral of the exponent of something very small. So instead of the integral, this is equal to the value of the integrand at lambda 0, the value at which the phase is stationary. So this lambda zeros. So I take the integral of the lambda by saying it's equal to the saddle point. So it's equal to the value at some particular values of lambda, so which are determined by some equations, and they correspond to some particular distribution of lambdas captured by this density. So instead of integrating over lambdas, I just evaluate everything at one specific point at large n. Well, the logic is a bit convoluted. Here it takes a couple of steps. Yeah. Any more questions here? Right. So, but what I want to say is that this object is defined at finite n, and I can still call it by the same name, g of x. This is okay. Finite. Yeah. Finite. Right. So let's try to rewrite our equation in the terms which are friendly to large n limit. So first of all, we just take this equation, multiply it by x to the power minus k minus 1. So then I can write it like sum L from 0 to k minus 1. So trace m to the L over xl plus 1. Trace m k minus L minus 1 over xk minus L. Sum, so k, no, it's not the sum. Wait, so so multiply by x to minus k minus 1 and take the sum k from 0 to infinity. So here I will get sum k from 0 to infinity of this n, and so correlator trace m to the k over xk plus 1 k plus 1 v prime of n. Yeah. So we just did a trivial operation. Take this equation, just multiply by new variable x to some power sum over k. Well, so we did this in order to get things like we have here, this geometric progression. So, you see here, these two powers, they sum up to k minus 1. So I can split my power here. So that I get L here and L plus 1, and here this and K minus L. So, so I think I'm a bit worried about some mismatch by 1 power. But hopefully it's okay. So you see what we have in the left-hand side. So this thing, this is exactly my resolver. So 1 over, so the n is also a bit off. No, it's, well, anyway, so what I want to say is I get this trace 1 over x minus n, trace 1 over x minus n, minus n, is that here, minus n, trace v prime of m over x minus n equal to 0. So this will combine into that thing, 1 over x minus m, and v prime is left out. Well, trace, you can move it in or out of the geometric progression, it doesn't matter. So this one is fine. So then here, this one is fine. This last one, I think, might have some mismatch by 1 power of x. I'm a bit worried about that. But, well, I think that should be fine. Also a bit worried about some powers of n. So this is 1 over n so this equation is a bit weird. So, well, okay, so I hope that the powers are all correct. So let's say as an exercise to collect all factors of n, and so rearrange the summations such that you get this. But this should be straightforward. Just I'm a bit not completely sure. There could be some typo maybe in one of the indices, but hopefully it's fine. So we get this equation, and so let's rewrite it in another way. So let's do the trick. Like, here we have the source trace v prime of m x minus m, which is a bit weird. So like we did last time, let's introduce the following object, call it p0 of x, is trace v prime of x minus v prime of m over x minus m. So we so assume v is a polynomial. So then this thing will also be a polynomial. So why? Well, the numerator is a polynomial of some finite degree. The denominator, okay, is a polynomial of the first degree. But actually, well, at the 0 of the denominator, the numerator also vanishes. So that means there are actually no poles, and this is some polynomial. Well, depending on many things, on the potential and so on, but still it's a polynomial. It's an object much simpler than our resolvent, for example. So, and if I add and subtract here this v prime, then I can rewrite this right-hand side in terms of this and in terms of v prime itself. So it's useful to introduce some notation like the following. So introduce some W of x1, x2 to be the this trace 1 over x minus m is 1 over x1 minus m, x2 minus m, connected part. So that is equal to the correlator of these two traces minus the correlator of each trace individually. And then, so for the single traces, we already have this notation, G, let me just rename it to W, so that it's written in a uniform way. And then, so then we rewrite this equation in the following way. So we get this W of xx, the first term. So I have to add this term that I subtracted. So plus to W, so I call this W2 and this W1 because it has one argument. This has two arguments, and in principle I can introduce this correlator of n traces, which would have n arguments, and I would subtract various connected parts. So this equation then looks like W2 of xx, so plus W1 squared of x. So and here I get n v prime of x W1 of x minus P0 of x. So what happened here in the right-hand side is, so I had this thing, then I added and subtracted v prime of x. So when I subtract v prime of x, I get this quantity. When I add it, I just have to add it by hand here. So since it's v prime of x divided by that, it will be v prime of x multiplied by this correlator, by the usual result. Okay, and this thing is just a polynomial. Yeah? Subscript here. W2, x1, x2. Right. C. So that's connected. To say that it's connected, I subtract the average of two traces individually, so that this has a nicer scaling at large n, basically. Yeah, so we get this thing. So that's still it is valid at finite n, but in this form it is much more nicely suited to taking the large n limit. So then, so what is this topological recursion? I will not derive it completely, but at this point we can see the general idea. So all of these quantities, they will have some large n expansion. So every W and k of x1 and xn, xk will be written as a sum. So let me see how the standard notation. Yeah, so as a sum, as a genus expansion. So n, well, it happens to be some concrete power, 2 minus 2g minus n, wg, well, minus k, wg, k. So they all have some large n limit, w0, k. And then there will be some corrections, like w1, k is the 1 over n squared correction, and so on. Well, also this p will have the similar expansion, and so on. So when you take the very leading term of this expansion, you recover the equation we had last time. well, which looked basically like so let me see. So we had it last time. Just to recall the notation. Yeah. Yeah. So So what happens here? So this W2, for example, this W2 is of order is suppressed compared to W1. It will be of order, I think, 1 over n squared. Because we discussed probably in the very first lecture that in the multi-trace correlator, the leading large n part corresponds to contractions within each of the traces individually. So at large n, this will be the dominant term in this correlator. And so W2 itself is suppressed by 1 over n squared. So at large n, this term is small. And so we find this equation W1 squared, well, equals, well, n is just some normalization, n v prime W1 minus P0. So this is a quadratic equation for W1, which we can solve, and we discussed all this last time. So depending on our potential, we more or less find this polynomial, then we find what is this resolving from consistency and so on. So that's just the n to infinity limit of this equation gives back what we had before. So this, by the way, is known. So this, since this is a quadratic equation, we will have W1 is like something plus minus square root. So one thing I forgot to say last time is that so since we have the square root, then it means we are working on some Riemann surface. So this Riemann surface is called the spectral curve. Of the model. So in this case, it's a square root of some polynomial. So this will be actually what's called a hyperelliptic Riemann surface. It doesn't matter exactly what it is, just a particular kind of Riemann surface following from this quadratic equation. Okay, so that's what happens at large n. So now what about some corrections? So for example, what about finding this guy, which is suppressed? So for this guy, one can write, so by invoking some rather simple arguments, one can say the following, this W2, x1, x2. So it will be, so like W itself, which is given by this integral, it's a function on this Riemann surface. So what are its properties? So it's going to have at large x, due to the definition, it's 1 over x asymptotics when x1 or x2 go to infinity. And also when x1 goes to x2, one can derive how it behaves. So basically by looking at the possible weak contractions, or by some other argument that I will not discuss here, we find that this W2 is has a pole of second order. Basically, it will be given like by an integral of this kind where there are two integrals with different free variables. And when they collide, there will be a singularity, which is more or less clear from this. So the precise form of the singularity will be a double pole. So in fact, these properties determine this W2 completely. So like W1 is determined from this equation, W2 is also at least in principle fixed. And for any given potential, one can write it in some more or less explicit form. So this is called the Bergman kernel. Which is associated in some canonical way with this Riemann surface, spectral curve, but it's, I mean, it's nothing that's fancy, it's just this two-point correlator, which happens to be fixed by its asymptotics and singularity uniquely. Yeah.
In the first one.
Yeah.
It was 1 over n, right?
Well, I mean, if you consider x1 going to infinity, so then, well, everything, it will need to have 1 over x1 asymptotics times some function of x2. That's all I want to say here. And similarly for x2, if they go to infinity independently, then you treat this part as a constant, and the asymptotics is right off from here will be 1 over it. So this function is fixed. So it may not be that simple to find it for any given surface, but it's like some completely fixed function. Well, and what happens afterwards is you just expand this equation at order by order at large n. And what happens is that all other w, either with more points, like x1 to xk, or with the higher genus, they are all determined by these first two, by this w 0, 1 and w 0, 2. So this w01 is our result, and w02 is this two-point correlator at large n. So, well, I will not do this algebra, but you just plug in this expansion into this equation. If you want to get higher orders of like w1, for example, then one can write the concrete result, which will be, let me see, blah, blah, blah. Well, just write the next order of this equation would be 2w01, because if I'm expanding the square to the next order in 1 over n, there will be 2w01. w11 plus w02 from this. Well, will be v prime of x, w11, well, they are all of x, minus p10. Well, so this p will be the 1 over n correction to this polynomial, but it will still remain a polynomial. Well, this is a linear equation for w11. Expressed, as I promised, for w01, w02, okay, and then some auxiliary objects, which are just contain a finite number of coefficients, so they again can be determined by invoking some arguments, like asymptotics and so on. So one has to impose some constraints to make this fully precise, but this is just the general idea. Then if you want W's with more external points, then one should start from more complicated loop equations with more insertions here, and then just rewrite it in the same way, and then algebraically almost one can read off all the higher W's. So this relation between different orders in n and different orders in the well, number of insertions, so this is what is known as topological recursion. So in practice, there will be quite a lot of technical details, like how you determine these polynomials, how you make sure that all asymptotics are satisfied, and so on. But the basic idea is quite straightforward, just large n expansion of these loop equations. Any questions here? Okay, so a comment about how all this is related to JT gravity, just a very, just to give a sketch. Let's see. So JT gravity is, roughly speaking, it's a two-dimensional gravity theory, or quantum gravity, in ADS, 2, with some boundaries. So we have a space which is hyperbolic but has some boundaries. It could be many of them. So parameterized by some, well, looking like that. So parameterized by some staircase surface with constant negative curvature, and cut it off at some places, such that what is left are some arcs of length beta 1, beta 2, beta 3, and so on. And then one is interested in evaluating the partition function, so just the functional integral on these surfaces. So it happens that these functional integrals, by some field theory arguments, they happen to satisfy exactly the same relations as the topological recursion, so in the number of these insertions. So more or less these betas, beta n, so they correspond to, so here we considered insertions of like trace m to the k, or these resolvents. So there they correspond rather to objects like exponent of beta m. But one can still write down the recursion relations in a rather similar way. And they happen to satisfy the same recursions as would the correlators of a matrix integral with some very concrete initial data. So like I said, everything is determined by this W01, 02. So in other words, by the strict large n data, which corresponds to some density of eigenvalues, rho of lambda. So which in this case is the sinh function, so precisely something like sinh of square root of lambda. Well, this density is not really nice, because remember previously we considered some density which would be like semicircle that would obviously have a finite integral, because the integral of the density is the number of eigenvalues. Well, so this density grows exponentially at infinity, so it's not really very well-defined object. But formally, one can still use all the tools, and then one finds the same recursion relations for the metric, just a single Hermitian matrix model, literally like what we discussed here, only one should consider these somewhat weird correlators and this weird density. And these relations happen to also coincide with what's known as Mirzakhani's recursion. So for the volume of the moduli spaces of these surfaces with the prescribed number of boundaries and lengths of the boundary. So all these objects satisfy the same recursion, and therefore, so one can also identify the boundary conditions in the appropriate way, and then this is how one shows that JT gravity is actually equal to this matrix integral. And well, and then this generated a lot of philosophical discussions why the gravity theory is integral over matrices, so maybe these matrices should be viewed as some random Hamiltonian. And then, well, so all of that also happened. Okay, so we don't have time to discuss this thing in detail. So if you want, there is a nice paper of Schenker, Stanford, and Saad which is quite readable. From 2019. It explains various steps in these identifications and all the detail. Okay, so so before we finish, just a couple of concluding remarks about matrix models in general. So one thing that I forgot to say that I should have mentioned in the very first lecture. So they often arise in localization. So localization is what happens when you have some functional integrals over some fields of some action, like in super young meals with some particular observables. It sometimes happens that this integral can reduces to an integral over constant field configurations for certain pretty complicated reasons. But for some special observables in supersymmetric theories, that's what often happens. And then these constant fields, if the original theory had the matrix fields like super young meals, they will be n by n matrices. And so it will literally be an integral over matrices like what we considered here. So that's why matrix models show up a lot in various supersymmetric calculations. And all these methods like large n expansion or topological recursion, they are all applicable there. So and the second two more aspects that we didn't have time to discuss are two very different representations of the partition function. Two different properties. So one of them is character expansion. So where you can write Zn as a sum over some Young tableaus, representations of GLN, and some characters. Well, I will not go into details of what kind of characters, but these will be Schur polynomials of these T variables, basically multiplied by some combinatorial factors. So this is a quite beautiful result that I don't have time to elaborate on, but just let me say that, so this connects matrix models a lot with the representation theory, because then at large n limit, the sum will be dominated by some particular Young tableaus, and so on. There will be some dominating Young tableaus will have some continuous shape that can be described by some equation, so this quite whole separate business opens up. And this representation is pretty different from the usual, say, perturbative expansion. And in particular, it's far from obvious that it will satisfy those Virasoro constraints. But it will. And the second comment is about integrability, since I mentioned it a lot. So this will be, one can show that this partition function Zn of t satisfies some bilinear equations. That is to say, they have products of z by z, so which involve shifts by n at the same time as, and also differentiation by the t variables. And then again, so they will satisfy bilinear equations known as some Hirota equations, also related to some integrable hierarchies for people familiar with this language, specifically to the KP hierarchy, for which they are what's known as tau functions. So, well, it's equations of the kind like the Korteweg-de Vries equation, which probably you heard has many integrals of motion and various nice features. So these matrix models as functions of t satisfy differential equations, in some sense describing time evolution in all of these t variables. Right, and so all of these features, they are very non-trivially related with each other. In principle, I could give quite a lot of lectures about each of them separately. But this is time to conclude now. So thanks a lot for coming to these lectures. I hope it was useful for you, and I'm happy to answer any questions.
So the localization question arises when people try to calculate the expectation value of over circular.
Yeah, for example.
Why
Yeah.
is it called localization?
Yes, localization, because of this very integral over a very large space of fields, it reduces to an integral over a very small space of just fields that are constants in space-time. So that is, people say that it localizes to constant field configurations.
And this constant coming due to the superposition.
Well, due to everything, like there is a lot of reasons why it localizes. In some sense, it's a statement that the saddle point evaluation of this integral becomes exact. Like we had the integral over matrices here, or over eigenvalues, so which actually reduced from just to summing over solutions to some over lambdas, which are solutions to some algebraic equation. So the integral over the whole space of lambda has localized to solutions of just a discrete set of points. Like so here, similar thing.
And it's not possible for any number of systems to do.
Well, I mean, it is very specific to certain field theories and certain is specific to certain observables in certain supersymmetric field theory. But there is a large class of them, like in super-Young Mills, in ABGM, in other models. Any more questions? Yeah. Hmm? Yeah. If you are interested in some references, feel free to email me and I can point you to references about various things. Yeah.
I guess some of the correlation.
Well, yes, yeah. But they are all actually also useful for gravity. For example, this integrability thing. So here in some cases, it's easier to compute 1 over n correction since it relates partition functions with different values of n explicitly. So then you can expand it in n, and it works nicely. Okay, thank you.